you've heard of calculus. Calculus is something that you'll have seen for the last, I don't know, 5, 6 years mentioned like a gloomy monster that's coming to get you. And well, today it comes. But it's not that scary. There's 2 parts to today, and neither of them is strictly calculus. We won't get into what was strictly calculus today. Instead, we're setting the scene for it. We're going to look at limits, which is something we've done intuitively, but we'll look at them a little more formally now. And then we're going to look at rates, or slope of a graph. And that slope of a graph is where we're going to spend a lot of the time looking for calculus, doing calculus. But to start with, limits. Now, limits in the textbook have this fancy notation, but sometimes it's just a really stupid example. So what this is saying is limit as x tends towards 4 of 2x plus 3. And when x gets really, really close to 4, this whole thing gets really, really close to 11. Because 2 lots of 4 is 8 plus 3 is 11. So it sounds really odd, but when x gets close to 4, the limit of 2x plus 3 gets close to 11. And you might notice that we've been talking about the behavior of functions. And so with the behavior of functions, we could easily have mentioned limits previously. For example, in the example you just did, there could well be a problem along the lines of y equals 2 plus e to the x. And you're looking at a horizontal asymptote. And we know that, if you graphed it, y equals 2 plus e to the x would look something like this. There'd be a horizontal asymptote at 2, and it would do this. And zoom on up. Yeah. And before what we've said is, as x goes towards infinity, y also goes towards infinity, and as x goes towards minus infinity, y goes towards 2. Yeah, this way and that. So we've used that language before. Limits can be used to describe this a little more formally. So we can say the limit of 2 plus e to the x as x goes towards infinity is infinity. So as x gets really high, the whole thing gets really high. And conversely, as x goes towards minus infinity, 2 plus e to the x goes towards 2. So we're not letting x equal infinity, we're saying as x gets very close to it, we'll equal to that. This does help us in some funny contexts. So take this one here. The function f of x equals x squared plus 5x on x. Now, we're resisting the urge to cancel the x out, even though I know we could. But we're looking at what happens to this function. So we know that we could probably factor out x and cancel x out, and we get a function that looks like this. But importantly, x can't actually equal 0. Because if x equals 0, we're dividing by 0. So we can't really understand what's happening to the graph at the point x equals 0. Instead, what we can say is that as x approaches 0, the limit of this graph approaches 5. So we would say, is it written there? Not written there. We would say the limit as x approaches 0 of x squared plus 5x on x is equal to 5. So it's letting x get very, very close to 0, but not equaling 0. And as it gets infinitesimally close to 0, this whole thing will equal 5. It's, I guess, language around one number or a variable tending towards a number. And so on the next page, we have a couple more examples. So turn over. And I'm going to do a couple of quick examples, and then you guys are going to practice them before we move on to slopes. first one, limit as x tends towards 2 of x squared. Any guesses what that is?
4.
Yeah, nice, 4. Answer for A is 4. 4. Right. Next one, as x approaches 0, what does this approach? Yeah, the answer would be 3. And the way we can show this algebraically for the limit of x approaches 0 of x squared plus 3x on x, we can rewrite that as limit as x approaches 0 of x bracket x plus 3 over x. And then because there's a common factor, we can cancel out. Normally we wouldn't be able to do this in regular day algebra because you can't divide by 0. So you wouldn't be able to divide by this if this is potentially 0. But inside the limit, we're saying x isn't 0, x just goes close to 0. So because it's strictly not 0, we are allowed to cancel this out. And once we've cancelled it out, we can rewrite this as the limit as x approaches 0 of x plus 3. And what we can do now is evaluate the limit. And evaluate the limit basically means we can we'll do a substitution. We can say, okay, well now x can go close to 0, nothing wrong with it being 0 here. So we let x be 0 and the answer will be 3. We couldn't do it straight away because on the first line, if we let x be 0, it would be like 0 divided by 0 and the whole thing kind of falls apart. So we couldn't have just evaluated the limit right at the start. We can't let x be 0 at this point, but we can do this because it's, going towards 0, and then we can evaluate the limit here because it's now allowed. Any guesses how we start with the next one?
6.
Was it
Limit
six?
is 0. Is 0.
I don't know.
It's 6.
Limit as x approaches 3 of x squared take 9 on x take 3. I don't think it's 3 or 6. Problem is we can't let x be 3 because if x is 3, the top number equals 0 and the bottom number equals 0 and it's kind of a mess.
Oh, you cancel it.
Yeah, we're going to aim to cancel, and I'm going to cancel by factorising in this case. So x squared take 9 factorises to x plus 3, x take 3, oh you're right, it's going to be 6, over x take 3, whoever said 6, well done, limit as x goes towards 3. And then we can cancel, because x isn't 3, it's going towards 3, and we're left with limit as x goes towards 3 of x plus 3. And there's no worries now with the making x go towards 3 and actually equaling it, because we're not dividing by 0 or doing anything scary. So then we can put that in, and we can say the answer is 6. Nice. Alright, so limits are a bit weird, but they are one of the sort of notations we need to be sort of comfy with for some calculus. So what I'd like you to do now is just start 14C.1 and we'll do a couple of those questions and then I will keep talking in a second.